if I draw a picture of the Earth, we know from physics 20 that that Earth, or any other mass, causes what we call a gravitational field. The gravitational field diagram surrounding the Earth would look like this. Field lines point toward the Earth. Now, why did we talk about gravitational fields in physics 20? Why didn't we just talk about gravitational forces in physics 20? Well, because the reality is, sometimes the Earth is there causing gravity, but there's nothing there to experience that gravity. And in the end, in order to have a force, you need something to produce it and something to experience it. Some of you guys may know, some of you guys may not know what actually causes gravity. Einstein said that the universe is really 4 dimensions as opposed to 3 dimensions that we usually talk about, the x, y, and z components that we usually talk about. He said it's x, y, z, and time. The 4 dimensions of what he called not space, but what he called space-time. And he said that whenever you have something that's heavy, like the Earth, for instance, in that fabric of space-time, now it's hard to visualize this, right? Because we see in the way that we typically talk about seeing, we see in 3 dimensions. That 4th dimension of time is a little bit different. So we can't visualize these 4 dimensions as well as we can visualize the 3 dimensions. But if we pretend for a second that this blanket right here, this fabric, is the universe, the fabric of space-time, if we put something heavy like the Earth on that fabric of space-time, then it's going to dent it. Right? We bend the fabric of space-time. Now, if all of a sudden we put a ball right there above the surface of the Earth, then it ends up sliding along the fabric of space-time. In other words, it ends up being attracted to the Earth. Right? That's why gravity does what it does. But it's this thing that causes gravity and this thing that experiences gravity that result in a force of gravity. In the absence of this thing that experiences gravity, there is no force. Right? There's no push or pull on anything if there is no anything to be pushed or pulled. But gravity isn't gone. Space-time is still bent. Gravity is still there. So how do we describe gravity when there's nothing there to experience it? We describe it as a field. That gravitational field that I drew a minute ago with the field lines pointing towards it. So gravitational fields are just a way of describing gravity when there is nothing there to experience a force. Does that kind of make sense a little bit? Well, we have a similar thing with electric fields. There are electric forces if there's something there to cause it and something there to experience it. But if there's no experiencer, we still have something. We still have electricity. So how do we describe it? Well, we describe it using this concept of fields again. Something that has a charge causes an electric field, whether or not there's something there to experience the electric field. We're going to define an electric field in a similar way to the way we would define a gravitational field. An electric field is a region in which an electric force could be experienced by a charged object. Why do we say could be experienced? Because there isn't necessarily something there to experience it. If there is something to experience it, okay, then there would be a force. Okay? In the absence of something there to experience it, there's still that electricity that we're going to call an electric field. Now, if we compare that to the gravitational field we'd define as a region in which a gravitational force could be experienced by an object with mass, right? So the region in which an electric force could be experienced by a charged object, or the region in which a gravitational force could be experienced by an object with mass. Now, an electric field, a little bit different than a gravitational field in one sense here, in that the gravitational field always points towards the producer. Always points towards the producer. There's only one type of mass, and mass causes a gravitational field to point towards it. But with an electric field, we can have a negative producer, which causes an electric field to point towards it, just like a gravitational field points towards it. But we can also have a positive producer where the electric field points the other way, outwards. We'll talk in a minute why we say it's outwards away from the positive and inwards toward the negative. But understand that with gravity, it always points toward the producer. With an electric field, it can point toward the producer or away from the producer, depending upon what type of producer, what type of thing is causing the field. So electric fields surround electric charges. Whether it's a positive charge or a negative charge, it surrounds electric charges. Electric fields are vector fields because they have a direction associated with them, right? We said it's inward if it's a negative producer, or it's outward if it's a positive producer. Gravity fields are also vector fields, by the way, because they also have a direction associated with them. Always inward, always toward the mass that causes the field. All of the fields that we talk about in Physics 20 and Physics 30 are vector fields. They all have a direction associated with them. They influence things, masses or charges, in a particular direction. But there are such things as scalar fields. A heat field or a light field influences things, but not necessarily in a particular direction. Electric fields, gravitational fields, exist as long as there's something to cause them. For gravity, it would be a mass. For electricity, it would be a charge, a positive charge, a negative charge. As long as we have something to make the field, as long as we have something to cause the influence, then we have a field. Forces, on the other hand, and Isaiah, this comes back to your question here. Forces exist only if there is something to produce the field and something to experience the field. Now, if we do put something in that field to experience it, there is a force, but that doesn't take away the field. The field is still there, but now we also have a force. If there's just the producer, well, then there is no force because there's nothing to be pushed or pulled, but the field is still there. So right up top here, right? Here's a producer, nothing out here to experience it, there's just a field. Here we have, whoops, sure, that should be a positive particle producing a field outwards, right? If we have a positive particle down here, still a field causing, or still a field that's caused by this positive producer. But now we have, let's say, this tiny little thing that's experiencing the field that also experiences a force. So just the producer, just a field. Producer and experiencer, you still got the field, but now you've got a force as well. We define the direction of that electric field in two ways, as we would define the direction of gravitational field in two ways. One, it's the way that a positive particle would move if it was placed in the field. If we go back to that last diagram that I had drawn for a second here. Okay, I got in this diagram an electric field drawn. I have it drawn outward away from this positive particle. Okay, why is it drawn outward away from this particle? Well, because if I put a little positive experiencer in there, which way is it going to go? Well, it's going to repel this guy, right? It's going to be pushed away from this guy. So if it experiences a force to the right, then by definition, the field has to be to the right, because we define the field direction as the way that a positive particle would move if placed in the field. What would happen to a negative particle? If I put a little negative there, which way would it go? Go the other way, right? So does the field point inward now? No. We define the field as the way that a positive would move if there's a positive there, not the way that a negative would move. We could have defined it as the way that a negative would move, but we didn't. The other way we define it is away from the positive and toward the negative. The reason I have this vertical line drawn here is just to separate these two diagrams so that you can see that they're independent of one another. They're not affecting each other. They're on opposite sides of the universe and not influencing one another. We're going to make this one a positive charge, this one a negative. We're going to make this little experiencer positive and this little experiencer positive. This little experiencer is negative and this little experiencer is negative as well. The electric field that surrounds this positive is this way. Number 2, we define it away from positive toward negative. The electric field that surrounds this one is inward. Again, number 2, it's away from the positive, but it's toward the negative. Why? Well, because if you look at this little positive experiencer in here, it would experience a force to the left right here. A force of repulsion from the positive producer. It would move to the left. Therefore, the field has to point to the left as well. Same direction as the force. Over here, which way is the positive going to be influenced? It's going to be attracted to this negative producer. The force is to the right. Therefore, we would define the field as being to the right. Negative particle up here? The negative particle would experience a force which way? Inward, right? The force is opposite to the field here. The field is pointing outwards, the force is pointing inwards. We're not going to change the direction of the field just because the force is pointing inward. It's a negative particle. The force is opposite to the field for a negative particle. Here we would say the force is outward. That's okay. The field is inward. It's a negative particle. The force is opposite to the field. I want to draw just a few diagrams here for general electric fields. The first one, we've already drawn. It's what we call a non-uniform field that surrounds a positive producer. Non-uniform, by the way, just means that it changes. It's strong. The field is stronger the closer we are to the producer. It's weaker the further we are away. It's a non-uniform field because it's not the same field everywhere. This is a negative producer. It also causes a non-uniform field, a field that is different depending upon location. The closer we are to the producer, the stronger the field. The further we are away, the weaker the field. And that should make sense, right? Of course, the closer you are to something that's causing something, the stronger it's going to be. Again, two separate diagrams. They don't influence each other. I'm going to make this one a positive for the top diagram, this one a negative. The field going away from the positive. The field goes toward the negative. Now, what I want you to recognize with this diagram is not so much the shape that you end up getting, but that when two things attract each other, as these do, right? These will attract each other. The field lines will join together. Sometimes you see a diagram on an exam that looks just like this, and you have to answer some question about it. But sometimes you see a diagram that you don't recognize. Like it's a new configuration of the electric field. Maybe there's 3 charges. Maybe there's different shaped charges or something like that's causing this configuration of electric fields that you've never seen before. And you have to identify which is correct and which is incorrect. Here's the bottom line. If the field lines in the picture that you see join up, like they do right here, there's an attraction. If the field lines don't join up, then there's a force of repulsion. We'd get a force of repulsion in a situation like this, where the field lines leave the positive, but then repel each other. And it looks something like this. So, going to have to remember these diagrams? Yeah, you know what? There's a good chance you will have to identify something about these diagrams on a test or an exam. But as opposed to memorizing these diagrams, let's just remember that if the field lines join, then there's attraction. If the field lines don't join, then there's repulsion. And that's going to take care of these diagrams for you and any other configuration that you might see on an exam that might be novel to you or new to you. Here's our last diagram for the day, at least, of an electric field. Is that a uniform electric field or a non-uniform electric field? This one's uniform. Field lines are drawn parallel to each other. This is a uniform electric field. Now, what causes this electric field? I don't know. Maybe it's two plates, two charged plates, maybe, whatever. Maybe it's some big massive positive, some big massive negative, whatever. It doesn't matter what caused it. This is the field. In this situation right here, in this localized area, we have a uniform electric field. Now, I want to look at what happens to positive and negative particles in different scenarios in this uniform electric field. So let's draw a positive particle right here. Let's say that this positive particle is at rest. It's not moving. I'm going to represent the force on this positive particle by a red line. Okay, force is red. Which way will the force be on this positive particle? Which way is the force? If the field lines point down, the force will point. I'm positive the force is with the field, right? Remember the quote? I'm positive the force is with the field. If the field points down, the force will point down. Agree? Now, what if, actually, let's have another particle in here first before I ask that what if. Now we got a negative particle. This negative particle is also at rest in this electric field, or at least initially at rest in this electric field. Which way is the force going to point on this negative particle? Up. I'm positive the force is with the field. So if it's with the field for a positive, it's against the field for a negative. Now, what if these particles were initially moving? We're going to draw an arrow on these particles in green representing the initial velocity of the particles, the initial movement of these particles. Let's say that this positive particle was initially moving downward. Which way would the force act on it if it was initially moving downward? Downward. I'm positive the force is with the field, whether it's moving or not. If the negative particle was initially moving downward, which way would the force act on it? Upward. Okay, negative particles experience a force opposite to the field, against the field. Doesn't matter if it's initially moving or not. What about this one? Let's say we got a positive particle that's initially moving to the right. Which way is the force acting on it now? Which way is the force acting on it now? Downward. I'm positive the force is with the field. If it's a positive particle, it doesn't matter what its initial conditions are, the electric force is in the direction of the electric field. What if we had a negative particle that was moving to the right initially? Which way would the force be acting on it? Upwards. Opposite to the field. Now, last question I want to ask you for the day. The last two questions, one for each of these particles. What would the path of this positive particle look like? It's moving to the right initially, but it experiences a force downward. Sorry? Go at some kind of angle? What other situation did you learn about in Physics 20 where something was moving to the right but experienced a downward force? Projectile motion, right? Projectile motion, good. Isn't this the same thing? Instead of a mass moving to the right off the edge of a cliff with a downward force of gravity, here we have a charge moving to the right with a downward electric force. The shape of that path is a parabola, just as Isaiah said. Now, what about this negative particle? This is projectile motion as well, right? Except that the parabola goes upwards. This is an inverse parabola. This is a, what do you call it? Whatever, right side up parabola. Normal. Does that make sense? Yeah, analyze this now essentially the same way. We won't do much of that kind of analysis with the parabolic path of it, but you would, if you had to, analyze it much the same way as you would projectile motion. X and Y components, V is equal to d over t that describes the x component because it would be constant velocity, but then you'd use some kind of acceleration equation to describe the y component because it accelerates downward or upward depending upon what type of particle it is.